Alrighty, so this is Unit 5 over Phases of Matter. This matches Georgia Standards of Excellence SPS5. This unit is looking at phases of matter, which is something that you've been doing for a really, really long time. But for the purpose of this unit, we're really looking at particle arrangement and particle movement. So the four states of matter that we are concerned with, the first would be solid. Next would be liquid. And we've got gas and plasma. Okay, so solids, liquids, gases, and plasma. Again, looking at, so the whole point of this is to look at particle arrangement. Okay, particle arrangement. For solids, they have a fixed shape and they have a fixed volume. Okay, so whatever size it is, whatever shape it is what it is. And when we look at kind of a particle movement diagram, they are tightly packed. I'm writing this instead of drawing it. Feel free to draw this on yours. So tightly packed, and they vibrate. So even the desk that you are sitting at right now, there is an element of particles vibrating. You're not going to get a massage if you stick your hand on it, but there is energy in those particles and they are vibrating ever so slightly. Liquids. Liquids have an indefinite shape. Okay, they have an indefinite shape, so they're going to take the shape of whatever container they are put in, but they have a fixed or a definite volume. Okay, if I have 20 milliliters of water, I can take that water, I can put it into a 100 milliliter beaker, I could put it into a 20 milliliter graduated cylinder, or I could pour it on the floor. I still have the same amount of liquid, it just takes the shape of whatever container it is. Particle movement wise, they are loosely packed. And I like to use the term flowing because, well, that's kind of what liquids do. They flow around. Gases. So gases also have an indefinite shape and they have an indefinite volume. Okay. Gases, they can take whatever shape of container they are in. And there is so much of it out there that we're not necessarily, unless we're in a closed environment, we're not necessarily going to have an X amount of gas present. And so gases have kind of this rapid movement going on, and forget the abbreviation there, but rapid movement for gases, and they are what they are. Plasma. Plasma is what we call an ionized gas. Okay, plasma is what we call an ionized gas. You see this word ion right here? When you see ion, you should think electron, right? Going back to periodic table and ionic bonding stuff. Ionized gas, what we do with plasma is we've excited the electrons. So they also have an indefinite shape. They have an indefinite volume, and it is this ionized gas. So lots and lots of movement going on there. Alrighty. So when we're looking at the states and the phase changes going from state to state, going from a solid to a liquid, this is melting. Going from a liquid to a gas, this is evaporation or vaporization. Going from a gas to a liquid is called condensation. It's that stuff that happens on the side of your water glass, especially in the south in the summer. And then going from a liquid to a solid, this is freezing. So as you see, going from the solid to a liquid to a gas, and I'm back up at this top chart, as we move from solid to liquid to gas to the plasma, we're doing nothing but adding energy. And you can see it in the form of this particle movement. So we go from the tightly packed and vibrating to the flowing to the rapid movement to this ionized gas, which for plasma, think like electricity, think fire. There's a whole lot of energy there. So going from a solid to a liquid, we are adding energy. Going from a liquid to a gas, we are adding energy. But as we start to reverse that, going from a gas to a liquid, at this point we are going to lose energy. And liquid to a solid, we're even losing more of it, as those particles stop moving as much and go more into that tightly packed and vibrating state. Okay, and so now the fun part for me about the phases of matter unit are the gas laws. Okay, this is where we kind of take and kick it up a notch from what you did in 2nd and 3rd grade and all throughout elementary school. So with gas laws, we have one thing that we're going to keep a constant, and it's comparing volume, temperature, and pressure. Now before we get into this, let's just do a quick little set of definitions so that we are all on the same page. When we're talking volume, we are looking at the space that is available. Okay, so the volume is the space available. This again is not a actual dictionary definition, but just something for us to think about. Temperature. So when we're looking at temperature, and I'm going to abbreviate here, temperature is a measure of particle movement. Okay. Yes, you'll see temperature, you'll think hot, you'll think cold, but in reality, it's a measure of particle movement. The less particles move, the colder we recognize that to be, i.e. ice. The faster particles move, the hotter it is. So you've got boiling water. You can physically see the movement of those particles going on. And then pressure. So when we're looking at pressure, I like to think about pressure as, and again, this is not the scientific definition, but it's maintaining a certain rate of movement based off of the size of the container. Okay, so I don't even know how to write that, but you think about like tire pressure. You're trying to make sure that the particles are bouncing off of that given volume at the same exact rate. You think about pressure in terms of your blood pressure. Your blood is moving through your body at a certain rate. So when we look at volume, temperature, and pressure and the relationship between the three of those, we're keeping one thing constant for every scenario. So right here we're starting out with the volume being constant. So volume being constant, think about the room that you're in right now. If we take, and you are the particle, and we tell you to start to sprint. If we tell you that you have to start sprinting, we are increasing the temperature because we are increasing particle movement. Well, you're in a certain room. The faster you start moving in that room, you're going to then run into stuff. You're going to bounce off the walls. You're going to run into your furniture. It's just going to be a total chaos. So therefore, the pressure is also going to increase in that scenario. Reverse it. If you decrease the temperature, so if you can move very, very slowly, you're going to be able to avoid all of the objects in the room that you're in right now. So therefore, you are also going to decrease the pressure that is in that container. Next one that we're going to look at is if we keep the temperature constant. Okay, so now we are keeping temperature constant. Temperature over here, measure of particle movement. So everything has to move at the same rate. Well, if we increase the volume and you've got particles that are sprinting around the room, if you were sprinting around, say, the gym, you've got plenty of space to move, plenty of space to run, so the pressure is not going to be nearly as high because it's going to take so much more for you to run into other people or to other things because you've got so much space. But let's say you don't have a gym. We decrease the volume to, I don't know, say a closet. Now if you are still moving at that exact same rate, it's not going to end well for you. You're going to run into everything you encounter, so therefore the pressure is going to increase. So, we'll talk about that in a second. And then our third and final constant is pressure. So when we have pressure as a constant, that means that stuff has to bounce off a wall at a certain rate. So if we increase the volume, that means that you're going to have to move faster because you have to move at a certain rate. So if we were to stick you at half court in a gym, or excuse me, if we're going to stick you in the middle of a classroom and tell you that you had to take and time how far you were going to run into each wall, and then you had to go into the gym and touch each wall of the gym in the exact same amount of time, you're going to have to move a lot faster. Whereas if we were to take you from, say, a classroom and just put you in the front office, we've decreased the volume. That means that you would not have to move as fast to touch the walls of the front office as you would the walls of the gym or your original time in a classroom. Alrighty, so the last thing that I'm going to hit here with gas laws is when you are looking at the relationship between volume, temperature, and pressure, we have what we call directly proportional. So I'm over here on the right, so direct, D-I. You have directly proportional relationships, okay? The scenarios where you have directly proportional relationships are when volume is constant and when pressure is constant, okay? So the direct proportional ones are for volume and for pressure, because whenever something goes up, the other thing goes up. Whenever something goes down, the other thing goes down, and you can see it here in this chart. Okay, the flip side of that is an indirect relationship. And in an indirectly proportional relationship, that is when temperature is a constant, because whenever the volume goes up, the pressure goes down, or whenever the volume goes down, the pressure goes up. So the indirectly proportional relationships are when temperature remains constant. Alrighty, so that is Unit 5 over phases of matter.